Hello friends, welcome to this video. In this video, I want to talk about why we need characteristic polynomial, because I just want you guys to get more interested in characteristic polynomial, and I want to connect you guys to the next unit, that is nothing but eigenvalues and eigenvectors. So in this video, we'll be doing simple example and some finishing touch to the unit 1, and I will just let you go to the unit 2. Okay, so why we need characteristic polynomial? Characteristic polynomial is what? That is nothing but the value of determinant of a minus lambda. This is nothing but the polynomial, right? If you solve this, you get a polynomial. Why we need this polynomial? What does it represent? What does it represent about that matrix? When I use the word matrix, matrix is what? Matrix is nothing but a representation of a transformation, a linear transformation with respect to some basis, right? Correct? Okay. You guys have learned this. So why we need this characteristic polynomial? So we know that a matrix representation will change as we change the basis. Let us see a simple example. Okay. So suppose I consider my matrix, my linear transformation from R2 to R2 over R, such that my T of x comma y will get mapped to x comma minus y. Okay. So I want to write the matrix representation for this. Let me choose the basis, ordered basis b dash is equal to 2 comma 0 and 1 comma 2. Okay, so these are nothing but the ordered basis that I am giving to you. With respect to this basis, I have to find the matrix representation of this. So what I will do, I will consider t of 2 comma 0. That is same as what? That is same as 2 comma 0 only. So that is same as what? Suppose I consider this as my E1, and this is nothing my E2 dash. Okay, so this is nothing but same as what? This is nothing but E1 dash 1 time plus 0 times E2 dash. That means in the matrix representation with respect to this, I will have my first column as 1 comma 0. Okay, with respect to some another one, that T of 1 comma 2. T of 1 comma 2 is same as what? T of 1 comma 2 is same as 1 comma minus 2. Now I want to write this in terms of E1 dash and E2 dash. So that is same as some alpha times 2 comma 0 plus some beta times 1 comma 2. So it is same as 2 times of alpha plus beta comma 2 beta. Okay, so what is the value of beta? Beta must be same as minus 1 by comparing this coordinate wise. So I got my 2 alpha minus 1 is equal to 1. So what should be the value for alpha? Alpha must be same as 1 then, right? So it is 1 comma minus 1. So I got to know my this linear transformation with respect to this basis has a matrix representation like this. Correct? Now let me just consider the standard basis. My standard basis B is nothing but 1 comma 0 and 0 comma 1, right? So with respect to this basis, it's really trivial. So it is 1 comma 0 will get mapped to 1 comma 0. So it is nothing but 1 times E1 plus 0 times E2. My T of 0 comma 1 will get mapped to where? It will get mapped to 0 comma minus 1, that is same as 0 times E1 plus minus 1 times E2. So the matrix representation of T with respect to this basis B will be what? It will be 1, 0, this coefficients, and for the second one, for the second column, it will be 0 comma minus 1. Okay. So what we learn? What we learn is, if I change this basis, if I change the basis, then my matrix representation will change. Correct? So this characteristic polynomial ultimately will help you to find out which is the simplest form, because if I consider this, I get this matrix like this. Is it a simplest form? No. Let me just give you the order. The simplest form of a matrix is nothing but the identity matrix, right? Identity matrices, which is just there for an identity maps. So we are not interested in it. After that, there comes the second most simplest kind of a matrix, that is nothing but diagonal matrix, that is lambda times I, some multiple of I. That is possible in some linear transformation, but not in all. The third type of matrices, which are called as a simple, are nothing but the diagonal matrices. Means the diagonal entry will be something and the rest of the entries are 0. That is nothing but our point of interest, right? These are nothing but diagonalizable matrix. This is what we are usually going to learn in unit 3. So for this idea, this is nothing but our question. Which matrices can be represented in the diagonal form? Like the way this matrix, means this linear transformation, can be represented like this also and can be represented like this also with respect to a different basis. The question is, does it always possible to diagonalize? Means, does there always exist this kind of a basis such that my matrix representation will be such kind of a diagonal matrix, or it will be always like this triangular matrix, right? So answer of such questions are obtained by solving the characteristic polynomials. The roots of the characteristic polynomials are called as characteristic roots or the eigenvalues. I'll just write on the next page. Okay, so this is important. Root of characteristic polynomial are called characteristic root. I will just write this much, characteristic root, or we call it as eigenvalues of that corresponding matrix. Okay, this you must remember because there is a quiz in the description box. Guys, just please go and give that quiz. It's just for you guys. There are 6 questions, a simple kind of questions, a few ideas you have to check. There are few of the concept that have asked in it. You guys have to prove it. Those questions should come in your mind. Okay, for any difficulty in the quiz, just write in the comment box, or you can write in the suggestion box in the quiz also. Okay, so for now I just give you the definition, what is called as a characteristic root or what is called as an eigenvalue. The roots of the characteristic polynomials are called as an eigenvalue. Okay, so these roots are really important. If I consider this matrix, first one, okay, I consider this matrix. The matrix was 1 1 0 minus 1. Okay, let me just try to find out characteristic polynomial for this. We know that I have given you a trick, right? In the video, I think previous video, there was a trick. Just go and understand the trick, remember it, it will save your time. So characteristic polynomial for this matrix A can be found out directly in terms of lambda as nothing but lambda square minus trace of A times lambda plus determinant of A. Quickly, otherwise you can go for this also, right? A minus lambda I is equal to 0. You should not consider it to be 0, but characteristic polynomial is this much, you have to find out this, right? So it's fine. So I will do it directly because you guys should remember it. What is the trace for this? Trace is nothing but 1 and minus 1, it is 0. So I'll write lambda square minus 0 times lambda. Trace is nothing but sum of diagonal entries, right? Yaad hai na? Okay. After that, plus the determinant. What is the determinant for this matrix? Determinant is nothing but what? It is 1 times minus 1 minus of 0, that is same as minus 1. So it is minus 1. It is same as lambda square minus 1. That can be written as what? That can be written as lambda minus 1, lambda plus 1. Correct? So in this case, my lambda is equal to 1 and lambda is equal to minus 1 are eigenvalues for this matrix. Correct? If you consider the other matrix also, that is nothing but 1 0 0 minus 1. Just find out the characteristic polynomial. Lambda square minus trace is again 0, lambda plus determinant is again minus 1 is equal to 0. That is same as the previous, right? So it is lambda minus 1, it is lambda plus 1 is equal to 0. So again I am getting the same one because they are actually representing a same linear transformation. Their eigenvalues must be same, my dear friends. There are few more observations that I will be reliving in the next video, but for now, thank you so much, guys. Whatever I want to just introduce to you, I have introduced. Now I want you guys to give the quiz, and in the next video I'll just continue with what I want to say. But for now, just go and give the quiz and wait for the next video. Okay, thank you so much, guys. Bye bye.